Good evening. Hopefully you're all entered and are muted. Please check your microphone to make sure you are muted. Otherwise, with the group this big, we get a lot of background noise. This program tonight will be recorded and hopefully uploaded to LCTV. So anyone who didn't see it and wanted to see it, you can tell your friends. They hopefully will be able to go to the library website, grab the link, and watch it on LCTV. Tonight, we are very fortunate to have Bill Vales. He's a local Littleton resident with a penchant for geology, and he's going to present on Oak Hill, Tophet Chasm, and the Smith property tonight. Take it away, Bill.
Okay, thank you, Helen. Welcome to everyone. I saw a lot of familiar names and a few faces, and that's great. My name is Bill Vales, and I am a Littleton resident, and I've been very interested in geology and really anything outdoors for most of my life. And I've spent a lot of time going through the geology of Littleton and also drawing on people in Littleton that have helped explain to me different aspects of the geology. And one person I would mention right up front would be Art Lazarus, who was a good friend of mine that I learned a lot from about Oak Hill, the Smith property, and Tophet Chasm from Art. So I just wanted to say that. Okay, the picture that we're looking at here is Lookout Rock. I'm just approaching Lookout Rock, which is not quite the highest area of Littleton, but it's close to it. It provides some magnificent views, which we'll see shortly. Okay, here's my approach. Not too scientific. I divided the town into two areas, the east side and the west side. Okay, on the west side was Oak Hill and the Smith property, and on the east side is everything else. And I used the map from the Littleton Conservation Trust to sort of map that out for me. Now, truth be known, Whitetail Woods should probably be on the west side, but since I'm not talking about that now, I threw it in the everything else bucket. Although I will say this, that you see this gash in the ground here, which is near Whitetail Woods. That happens to be the Sandville pit, or whatever the company is called now. And that has a significant part to the geology of this area, okay? So, okay, Oak Hill, it's near Littleton Depot, about a half a mile from the junctions of Route 2 and 495. So when you park there, you get to hear all that road noise. But boy, once you get into Oak Hill, that all goes away, which is really, really beautiful. About 220 acres, beautiful mixed wooded property, interesting geology, and 6 miles of hiking trails, maybe even more. And I will say this about the hiking trails, they are in magnificent shape, magnificent. Summit Rock is the highest point in Littleton. It goes to 505 feet. Lookout Rock, which is a little bit lower than Summit Rock, provides expansive views to the east to Boston. Okay, so for a little stroll with little effort, you can get some beautiful views, and you'll see that. Another interesting point, Tophet Chasm is considered a temporary outlet for glacial Lake Nashua, which was about 15,000 years ago when glacial Lake Nashua drained out. And one of the things we need to keep in mind is the Ice Age, the Ice Age, the Ice Age. It's the last major geological event that's happened in this area. So a lot of what we see here is influenced by glacial deposition, okay? And we'll talk more about that. Another feature of Oak Hill, which will mean nothing right now, we are on the northwest side of what's called Shrewsbury Ridge, okay? And that's a ridge that really extends from Oak Hill, which is the northern terminus, down to Shrewsbury, and that'll become significant in this story. Oak Hill also has some historic stagecoach roads on it, which are neat to see. Okay, so here I am leaving the highest part of Littleton, Summit Rock, and I'm walking down to Lookout Rock here. And I'm approaching Lookout Rock. This is the same picture that I showed you on the cover slide. And my view from Lookout Rock is really intense to the east, okay? I can see Boston with the naked eye. I could see the Prue and the John Hancock building. And it's really a beautiful view. This was on a late fall day, probably November, just looking at the leaves. So, but we're here to talk about the geology. So now here I am on Oak Hill Road, okay, which is just below Lookout Rock, and I'm looking up. And where I was when I took that previous picture, you see where my cursor is here? I was about here. Now, on Lookout Rock, you can see here some stumps here. The town took down a whole bunch of trees a few years back to open up this view. There's two types of rock here. We have this gray granite, which I'll get a little more detailed about shortly. And to the right, we have this, it's called muckbrook schist. Okay, so it's a type of schist, and it's named muckbrook. And typically rocks, they're named after areas that they were found in. So muckbrook schist was probably found in muckbrook in Westford, Mass, and hence the name muckbrook schist. Similarly, this is another view of this these two rocks, and you can notice here the point of contact between the granite, which is over here. This, by the way, is granite, A-Y-E-R, granite, which is the same granite that's in the Sandville area. Okay, I'm pretty sure it's granite. And to the right here is the muckbrook schist. And I think you can sort of see on the muckbrook schist, there's a little bit of foliation. If you can see lines, sometimes you have to look at my window because I talk with my hands, but you'll see lines over here, okay, that give you a little sense of the foliation. Now, interestingly in geology, interesting things happen at points of contact, okay? So when two rock types meet together and they're at a point of contact, that's an interesting place to look for stuff, okay? And we'll talk more about that. This is Lookout Rock, a little bit up close and personal, and this is what convinced me that this is similar to the granite at Sandville, because I had a lot of the resources I used are from the U.S. Geological Survey, and I was able to get the quadrangle, which is the unit of the blocks, if you will, that geology work is done at. And the quadrangle had a beautiful picture of granite, and it looks a lot like this. So what do we see on this granite that's unique? Well, first, it looks like it has fairly large crystal size, okay, meaning granite is composed primarily, let's say three types of minerals, quartz, some feldspar, and usually a black mineral, maybe like an amphibole or a hornblende or an epidote, something like that. And just looking at this, I can tell that these minerals are, the crystals are fairly large. They just look that way, that I can see them with my eye. They're actually called porphyritic, that if you can see the crystal with your eye, it's known as a porphyritic crystal. And here we are a little bit closer. You'll notice that, you know, to do geology, sometimes you got to get down on your hands and knees. And this is what I did. You get down on your hands and knees and you start looking for minerals. Because when you find certain rocks, that's kind of neat, but it's also neat to find the minerals that are within the rock. Okay, and what I'm finding on Lookout Rock here is, here's a black mineral, but I see a little bit of green on it. I've been noting, I have to go back up to look at this again. But I'm thinking that this black mineral is either a tourmaline, an epidote, or a hornblende. Okay, and I'm kind of leaning towards, I'm not sure what I'm leaning to now because I just confused myself. Um, so there's a whole string of these black minerals there. Now, here's another mineral that we see there. This is a sheet of mica. I'm sure we've all seen mica, little flecks of mica. I have pieces of mica that are like a foot square, okay, that I've found in places in southern New Hampshire. Okay, but on Lookout Rock, there are little bits of mica. Now, this is clear mica, which is known as muscovite mica, but another primary mica that we find around here is called biotite mica, which tends to be black or brown a little bit. And the tip of my instrument here is a pen, just to give you a sense of the size. And all around here are feldspar crystals and quartz crystals. So this just looks to me like a pegmatite, porphyritic. I can see the crystals with my naked eye. I don't need a loupe, although a loupe is useful to have. You know, that's always good to have. And if you start looking, this is almost looks like a gem quality garnet that I found out up on Lookout Rock. And I think it's an almandine garnet looking at the shape of it. And the garnet has, I'm going to give you a lot of terms in this talk that you're going to say, what the heck is he talking about? So just take notes, you know, and it'll give you something to look at, or you can send me email later and we'll talk more about it. But this crystal has 12 sides to it. It's called a dodecahedron. Okay. And this was so well formed, I could see about 10 of the crystal faces on it. And the ones that I couldn't see was because that's where it was affixed to the rock. Okay. So there's some interesting minerals to see along with the rocks. Okay. And this is like a classic pegmatite. This I found just off Lookout Rock a little bit. This doesn't really look like a granite. And the reason it doesn't look like a granite to me is it doesn't have, I don't see a lot of quartz in it. I see a little bit of quartz in it, but not a lot of quartz. I see this white material almost looks like a white feldspar known as an albite. But I'm not sure. But you can see here, look at all the garnets in here. They're not as gemmy looking as that other one. And there's your black mineral. This is probably a hornblende or something like that. So, and you can see the size of this sample with the quarter down here, the arc of the quarter. So those are a few of the minerals of that. Now, some features, I'm going to be talking about features, and rather than doing like a geology 101 and having to start here and go here and here and here, I'm just going to introduce, you know, I'm going to basically take a walk through Tophet's Chasm, which we're already doing. And as I walk through it, I'll introduce various concepts and things of that nature, and you can, you know, take notes on them and, you know, do whatever. But so things we're going to hear about Oak Hill. So that's the general area that we're talking about, Oak Hill. Within Oak Hill is Tophet Chasm. Okay, that's part of the Oak Hill conservation site. Now, Oak Hill itself is part of a terrain called the Neshoba terrain. And it is that area that you see here in, it's kind of a light green, I think it comes across as. Okay, light green. And you'll notice, and this box here is roughly where we are focused. We're actually a little bit below this line. Okay, we're a little bit below this line here. Okay, so the Neshoba terrain. So this was a large block of earth that moved off of the prototype of Africa, which we'll get to in more detail, and eventually docked up against North America. So we're going to talk about Neshoba terrain. Then muckbrook schist. This is a very unique, well, it's a unique type of schist in the sense that it's found pretty much within this box and a little bit to the north is what my reading, not quite up to Lowell. And the Tadmuck Brook schist, which is all over Oak Hill Road, is indicative of when two continents came together and one subducted under the other. And when I say subducted, I mean the Neshoba terrain went under the what's referred to here as the Merrimack Belt. Okay. And how do they know that? They know that from the minerals that we find in the Tadmuck Brook schist. Okay. We know that. And we have a pretty good sense of the depth that those were created at. And I'll talk more about that. The Clinton-Newberry fault is this line here, which bounds, let's say, the north or the western part of the Neshoba terrain. And typically, when you think about it, you have these separate blocks of land that are moving across an ocean, and they're going to join up against a continent. At every point these terrains join, it creates a fault. Okay, a fault is created. And that's why we have here the Clinton-Newberry fault. And this actually runs from eastern Connecticut up to Newbury, Massachusetts. The other side of the Neshoba terrain, the eastern side, is bounded by the Bloody Buff fault. Okay, and you can see exposures of that in Lexington, and that too terminates up around Newberry, Massachusetts. Okay, and within the terrain, all the rocks are similar. They're not identical because some of the environments that generated the rocks was a little bit different, but it's all considered to be the same assemblage, so they consider it the Neshoba terrain. Okay, and then you always have to consider, and I'm being redundant, that glacial dynamics washed over this whole area. Okay, from 2.5 million years ago up to about 11,500 years ago. Littleton had the better part of 2 miles of ice over us. Okay, 2 miles of ice. That takes a lot of water out of the ocean, and it's heavy. So it really pushes down on the land. So you need to think of, those sorts of effects by it. Okay, so here's a picture of Tophet's Chasm. So I've just walked in Tophet's Chasm. I just want to give you a sense of things. And beautiful hemlock forests on the south south side. I just love the hemlock trees that are here. And you can sort of see down here, maybe it's in my mind's eye, but you can see a little bit of water down here. Okay. And I'm up at a point, I'm probably 80 feet away, thereabouts. But this would be if I slip, this would be a slow roll down there. Almost looks like it would be a comfortable roll based on where I'm looking. However, this is me up the trail a little bit and down the side that we're just looking down, only in a different point. And this would not be a good area to roll down. This is loaded with Tadmuck Brook schist. Okay, that is really tortured looking. And by tortured, I mean it's been stretched apart, ripped apart, tipped over, and it's really very tortured. And then you get to the bottom, Tophet's Chasm. And this I took, I think, on April 7th. I think that's when I was there, April 7th, there last. And it's wet. It's a swamp down the bottom. It has some beautiful vegetation. And even on April 7th, I was really hearing some early bird song, which was nice. So quiet, couldn't hear any road noise, no people. Everything about it was good. The point that I gotta bring up that you have to remember, note, there are no rocks down here. There are no rocks, okay? When I say no rocks, I mean Well, there's no rocks, no big obvious rocks. Okay. Now, some things to keep in mind. I'm just going to go through here like bullet lists. Keep in mind when I go into the field, compass directions. You want to have a sense of your cardinal directions on the compass. Why do you want that? I want to know which way the ice came. I want to know which way the ice went, and I want to know which way plates moved. Okay. So I want my orientations of east, west, north, south. I need that. Always be aware of your rock types. This may require a little bit of study, but you have your three main rock types. You have your metamorphic rocks, igneous rocks, sedimentary rocks. We'll start with sedimentary. Those are rocks that would be deposited in the bottom of an ocean, the bottom of a lake, a bottom of an embayment. You can think of little particles raining down, maybe dead sea animals with calcareous shells raining down. Eventually that piles up, it gets pressed down, compacted. It's called lithification. That produces a sedimentary rock. Then you have igneous rocks. Igneous rocks are rocks that have been taken to a completely liquid state under incredible heat. You can think of them as volcanic, and the results of the volcanic rock, if it's an extrusive, meaning it comes out of the earth, it's going to be a volcano like we see in Hawaii, okay, where the lava comes out of the earth. If it's intrusive, then what happens is the rock or the granite is formed in place under the earth. Okay. And in time, through erosion, it'll eventually come to the surface. It's not that it comes to the surface. Well, it comes to the surface a little bit, but it's like the surface is removed, right? And comes down to the rock. So, so those are your three rock types. And then I think of the rock cycle too. Whenever I look at a rock, and I learned this from someone when I took some courses at Boston University in geology, that when you look at a rock, consider the type of rock that it was before it's the rock right now. So for instance, I look at the muckbrook schist, and I see a lot of clay particles in there. I see silicate crystals. I see a lot of mica. Okay, there's a lot of mica in it. And that rock actually came from a seafloor. Okay, and when the continents were moving together, some of that rock was scraped up into a seafloor. And then when it's pushed down into the subduction zone, okay, it gets turned into the muckbrook schist. And schist is a fairly it's early in the metamorphic cycle of producing rocks. If you think about it, when rocks, if they go down into the earth, the deeper the rock goes, the more it'll tend to melt. But remember, metamorphic isn't completely melting. Schist doesn't quite go to the level of either the depth or the pressures that some other rocks would. Always keep in mind the environment was different, meaning the atmosphere and the climate. We didn't always have all this oxygen in the air and nitrogen and methane. It was different, and that makes things different. I always think about my plate tectonic setting. I'll talk more about that. I want to go down to this item right here, post-glacial. When you're looking at something, yes, the glaciation is the last big geologic item that we see, but the next big item that we see as what man has done to the land, both in terms of farming, building things, excavation, and then of course we have the general erosion and deposition that still continues on geologically, and vegetation, which just covers everything. We'll talk more about these 2 points below when they come up. Okay, this is the best Lidar map I've seen of Oak Hill. I got this map. Lidar is a technology that uses laser, and it bounces laser off the ground and produces these terrain maps. And you're seeing more and more of these terrain maps. You saw it, the Littleton Conservation Trust has that terrain map that we saw at the beginning, but this one's great. So I got this from, I took my nephew up here who's a geologist. So he had lots of resources to Lidar maps way back when. So he pulled this baby out for me. And right away, I want to, so this is Oak Hill. And it kind of, to me, it looks like a foot on the right side here. Here's the big toe, and there's a few toes down there. But I want you to note here that Tophet's Chasm is really running in a northwesterly direction. Starts from the southwest, goes up to the northeast. Okay, southwest, northeast. I want to make a point. Remember I said, know your compass direction. Well, the northwest is up here, and this is the general direction that ice came down from the north during the last ice age. Okay, that says to me that the ice did not excavate Tophet's Chasm. Okay, since the direction of the ice flow is actually perpendicular, okay, to Tophet's Chasm. So, so that's my comment on that, and my comment on why it's important to know direction. Now, Mark had marked this up. He had got my, that's my nephew's name. He had sent this back to some of his geologist friends, and they looked at it, and they immediately recognized water flow going on in here. And they highlighted this picture with several, the blue lines indicated where they saw water flow in here. And there were also other points that they made. The pegmatite intrusions. Here we are at Lookout Rock up here. You can see a little bit of the Sanderson esker over here with the kettle hole. These are part of the glacial landforms that we get. And I added here Oak Hill Road and Harvard Road. Now, one point I would make is this general format makes me think of what's called a roche montagne. Okay, roche montagne. That's my poor attempt at trying to sound like I can speak a foreign language. Another term for that would be sheepback or Stoss and Lee topography. But if you look at this, this is classic Stoss and Lee, where ice would move this way, and it tends to move up bedrock in a very smooth sort of way. And as it comes down in the direction it's going, it starts plucking the rock off the direction it's going. Classic forms of this is the old man in the mountain, where the old man doesn't live anymore. That's a roche montagne. Okay, this I believe is another roche montagne. And in fact, I'm seeing that structure at this level, but if you walk around and just look at individual rocks that are oriented in the northwest direction, you can also see some roche montagne structures there. So we have to talk a little bit about plate tectonics. I think the picture of plate tectonics is at one point all the continents were together, okay, and then they've moved around, okay, until they get back to until they arrive at our existing part that they are today. But look at this picture here. This is just trying to get you to look at the concept. This started 225 million years ago. That's not nearly far enough to get back to what to the Littleton story. Okay, the Earth history goes back 4.5 billion years. 2.25 million years. That's a drop in the bucket. So we got to go back a little further. So in this picture here, we're going to go back about 500 million years, 490 million years. And I'm just going to quickly go through this, but bear with me. I think I'm going to give you all the information you need. Starting here at 490 million years ago, which is in what's called the early Ordovician period. And remember, there's still 4 billion years of history in front of this, okay? But at 490 million years ago, take a look at this. This SP represents the South Pole. So at this point in time, what we think of as Africa and South America, they were formed into one continent that was called Gondwana. Okay, that's what it's referred to. And that was stationed on the South Pole. There were there were probably more, but there were at least 4 significant terrains that were off the coast of what we think of as Africa. And up here is something called Laurentia, which is the prototype of North America, the prototype of North America. So let's go forward 40 million years. You can see now that these terrains have moved off of Gondwana, okay, and have started working their way towards Laurentia, okay, and also Balticia, this little piece of land here, is also moving, okay, because these plates are always moving around, okay. They're on a very viscous material. It's called the asthenosphere, and on top of that, we have these more rigid lithospheric plates called the lithosphere. Okay, so now let's look at this, the third globe. We're up here at 425 million years ago. And now note the orientation. Here we have the North Pole here, okay? And we see these 4 terrains moving into position, and they're coming up on the prototype of North America here, Laurentia, okay? And then at 400 million years, they've locked into Laurentia here. They've actually seized. And we have here the Merrimack terrain, the Neshoba terrain, the Avalon terrain, and the Maguma terrain. Now, this is the way Laurentia looked, the brown part, okay, which had like what they refer to as the stable craton, the stable bit of bedrock that made up North America. But as continents, and continents have been moving around for 4 billion years, okay? So we've had many supercontinents, but this is the picture, okay? We have these four terrains that have left what we think of as the west coast of Africa, and they've moved in place. And here's the Merrimack terrain, boom, moves in. Here's the Neshoba terrain with Littleton on it, boom. Here's the Avalon terrain, boom. And then here's the Maguma terrain. So they've all moved in succession. And as they're moving across the ocean, they're colliding and bumping. So there's some dynamics going on between them. And during its travel, there may be volcanoes being produced and other things. And those are coming right in too. So it's like the volcano has been made, 1,000 miles to the west, but we're going to ship that, right in 1,000 miles to the east. So that's a general a picture of this. So 3 points on this slide. The primary rock formations we're going to be talking about here are granite pegmatite, Neshoba formation, which is the primary formation of rock in the Neshoba terrain. So we have the Neshoba terrain, and the type of rock is the Neshoba formation. And then we have the muckbrook schist, which is all part of the story. Okay. Now, the Clinton-Newberry fault here, as I mentioned, you can see now perhaps a little clearer that when these terrains lock in to Laurentia, you can see where there would be a fault on either side of the terrain. And in fact, the faults, it's really not a clean line. There's a whole network of faults, within here. This is a very faulty place, okay, all through here. There's systems of faults all through here. Now, they're no longer active, but at one time it may have been a fault, what's called a right lateral fault. I don't want to get into that, but it's called a right lateral fault. And it may have been similar to the type of fault system at the San Andreas fault, similar to that. It's possible. Okay, here we are. I'm going to walk into Oak Hill. Now, this is right off of Oak Hill Road. The first thing I'm struck by when I walk into Oak Hill, and you can see the little service road here, is this rock. This is Tad Brook schist, okay? This rock looks incredibly smooth, incredibly smooth. All the rock right around this area looks very, very smooth, like it was worked by water, perhaps, okay, or ice. I suspect water was the final agent that worked that. And how smooth is it? Look at that. That boulder's as big as my car, but that's smooth. Tad Brook schist. And when you're looking at rock, just be mindful of that. Sometimes you're looking at organics like lichen or moss or the results of acid rain. So sometimes you need to really see the rock. You need a fresh break on it. But unfortunately, a fresh break breaks the rock, and I hate the look of broken rocks, so I don't break them. So this is very, very smooth. And you can see some of the foliation planes, okay, meaning as this was compressed this way, it lined up all the minerals this way. And that's where those foliation patterns come from, which may be different than what's called the bedding patterns. Okay, so here I am. I'm at Tophet's Chasm, and I have to do, well, I'm approaching Tophet's Chasm. And if I take a left here, I'm going to go on the yellow trail along the south wall, the rim. And if I go straight, I'm going to go down this orange trail. See the orange right there? And I'm going to go down to Tophet's Chasm. So here I go. So just want to remind you, this is where we're going down. And I'm right about here, I think, roughly right about here. And I'm going to go down, and I'm going to walk to the end, and I'm going to look around, and then I'm going to come back, and then I'm going to walk around in the chasm, and then I'm going to climb up this north wall here, and then I'm going to play around a little bit here, and then I'm going to walk back here and be up on the rim. Okay, as I walk out. So that's my path. Okay. So as I go down to Tophet Chasm, I'm confronted right away with one of these channels, which is really very interesting. There's probably 8 or 10 of these channels that you'll see, not just on the south wall, but there's others on the north wall as well. And then at the bottom, I encounter this recumbent fold in a piece of Tad Brook schist. Now, you may ask, what's he talking about? I don't see anything there. I just see a rock. Well, looking at this rock, what I could see was that this was a piece of rock that was broken off, and we were fortunate enough to still have the apex of the fold in here, okay? So this rock was actually bent over, under pressure, okay, under pressure and depth. And because of that, it did not break. If you tried to do this on the surface, it would break. This did not break. This is, this made my day, quite frankly, when I found that, okay, and opened up a whole new world of folds to me, okay. So here I am at Tophet's Chasm, and it's wet. And like I say, it was April 7th. I'm down there. It's wet. And I'm walking towards the end now, and I can see I'm pretty much at the end. I can sort of make out the house here. And there's no rock down here. There really isn't rock. There's mud and peat and things like that, but there is no rock to speak of. Plenty of rock on the wall. So now as I'm walking back, I have the left wall, the south wall on my left, and I'm walking back, and now we start seeing some of this tortured Muckbrook schist. And doesn't this look a little different, like it's in a little different posture than the rock that we first entered here? This looks like it's been torn up, thrown around, and just like it's been in a fight. Okay, highly tortured rock. You can see here some pieces of bedrock. This is as big as a truck. Okay, up here. Here we see pieces of rock that are on edge. Now, rock is not laid down. Rock is laid down flat. Okay, so to turn things on edge requires some tremendous forces. Okay, and one such tremendous force would be plate tectonics. Okay, that would generate the force to do this. Look at this. Okay, this is as big as a pickup truck. This is on edge, and this has what's called a dip of 90 degrees, meaning this rock enters the earth at a 90-degree angle. And that's useful for geologists when you deal in terms of strike and dip. Okay, so something moved that rock to a dip of 90 degrees. And then as I walk along, I have all this chaos on my left, okay, of this rock. And on my right, I have these beautiful trails, which people keep these trails in great shape, and there's no rocks in the chasm on the right. For the whole length of it, there's no rocks. So I continue on and I get to the head wall of the chasm, and I start seeing a few boulders here. Okay, from the head wall, you can sort of see it. And the head wall loses a little bit of steepness, not much, but a little bit of steepness. It kind of tapers out a little bit. So now I climb up the north wall, and I sort of stayed on the trail there a little bit. And you see here again, once you go up the wall, this is on the other wall now, the rock is chaotic. It's been broken. It's been smashed. It has this dip at 90 degrees. And you see some more chaos here. Okay, this is on the north wall. Actually, just a little bit above the north wall. Some more, this little things on edge. And by the way, I found a geocache. I'm getting pretty good. I found a geocache there. Which is on the north wall, which I won't tell you about. Well, I won't tell you exactly where it is. Well, I guess I did. I said the north wall. Okay, so here's some Muckbrook schist that really shows the lamination and the foliation, and you can see a little bit some of the sheen of that rock, and the sheen of that rock is a result of the mica that's been ground up, okay, and incorporated into the rock when it was subducted down. This is on the north side, a large piece of Muckbrook schist there. And if you really look at this, there is some very interesting folding in this rock. I spent about a half an hour the last time I was there looking at this, and this requires a couple more hours look. There's some interesting stuff in that rock. I say that to you, Bill, next time you're in there. Okay, so now I'm walking around. I'm walking around, and this is at the head wall, and we see the head wall now. I'm pretty much facing due east, and the head wall, it looks like one of these channels. Okay, it looks like one of these channels again. So I continue on. So how did Tophet chasm form? Okay, so here's two ideas, and I've had to go back and look at a number of papers and resources. But in 1930, a fellow by the name of Irving B. Crosby put out an idea of keystone faulting. And it turned out that he was a local geologist, and so was his father. I forget if this is the father or the son, but it was a father-son pair. And here's what keystone faulting is. And this is the idea that tophets, this was actually rock that went completely across. Okay, there was no chasm there. And what happened was that during some plate tectonics movement, because of all the fault system, the rock literally fell down. Literally fell down. And this is a common thing that happens in rock. It's called horst and graben. Horst and graben topography. You see a lot of it out in the Basin and Range, Nevada area, but it's actually fairly prominent in New England. So keep that in mind for this little description. So, whoop. Okay, so here we are. Here's the view of, the two lines represent looking down the map view at the chasm. Okay, now time one. Let's say I'm at the end of the chasm and I'm looking at a cross section. Okay, so at time one, there was just solid rock. Okay, no chasm existed at all. Okay, so this is the view from the outlet of the chasm. At time two, after there's been, remember, there's lots of, you have these terrains that have been moving in, compressing against Laurentia. You have several issues of, several incidents of mountain building from these terrains moving in, putting pressure on the rock in front of it. And during time two, this rock fractures because of tectonic changes, okay? The rock fractures. Maybe the tension that was holding it up lessened, okay? And literally the rock dropped. Boom, time three. The rock drops, providing a keystone. And this is a keystone fault. Okay, so, and this is called a graben. And again, horst and graben is a very common geological formation. Okay, so that's one idea. Now, I'm thinking this probably happened, I don't know if it happened, this is a guess, 300 million years ago, maybe something less than that, but a long time ago. The second idea is a plunge basin. Okay, and Richard Lugie, who in 1956, a professor at, I believe, Clark University, postulated that Tophet Chasm actually presented an outlet, an outlet for all this water that was building up from this monster glacier that we had in front of us. And Tophet Chasm then became the outlet for that and created an incredible outflow of water that just raced through the chasm, pushing everything out. And that's why we don't see rock. Now, here's the picture that Lugie used, that you have this large retreating ice cap, and here you have Tophet's Chasm over here. And it's interesting that in Lugie's picture here, he assumes that the chasm is already there. That's an interesting thing that had just dawned on me today. He's assuming the chasm was there, because I would ask myself when I'm down there, well, if the water went through the chasm, why didn't it go, a mile down the road or a mile up the road? Why'd it go here? And it probably went here because this was an ideal spot. It was already excavated out. It was already excavated out if the keystone fault occurred prior to the model of the plunge basin waterfall. So that's my thinking there. Now, I'm walking along the south wall looking down, and it's really a beautiful trail. There's a few roots and everything, so you have to sort of, pay attention to what you're doing. Again, beautiful hemlock, and you see the yellow blazes here. Okay. And I start crossing these drainage patterns again. Okay, just keep on crossing them. You're always going to find some glacial erratics okay, along the way. There's a couple that I run into when I was going out. One is this nice mixed erratic. It looks actually like a pegmatite mixed with basalt. If you really look at it, you're going to see that there's multiple rocks in there. This one is called egg rock, I believe, which I saw coming out, but I turned around to take this picture. You see some nice, this looks like quartz veining that's underneath. And then on the other side of the chasm, I put this in because it's just aesthetically nice. It's a Buddha rock, which is a great example of mechanical weathering that probably calved off that piece. Okay, so here I am back to where I started when I went down the chasm. And now I'm going to walk out. And as I walk out, I'm reminded about these large boulders that are not as chaotic as what I saw in the chasm. These are beautifully smooth rocks, okay? And this little rock here, which I've been doing some work on for years now, maybe I'll finish it, I don't know, but reminds me of some more smoothing, but it also reminds me of the folding that goes on. There's a little bit of folding. You know, folds don't have to be as spectacular as the one I showed. They can actually be very tiny. Okay. Now, from here, just to remind you, this is the extent of the ice. Okay. About 2.9 million years ago, extended up to about 11,500 years ago. And there were several successions of glaciations, deglaciations, glaciations, deglaciations. So kind of an ebb and flow. But there's Littleton, pretty much up here where the star is. And that was covered with ice, covered. You get all these landforms and more from ice. You get drumlins, eskers, moraines, and we see all of these in Littleton. You want to have a study in in moraines. Go down to where that new gravel pit has opened down by the electric company, and you'll see gradations of delta formation as it's been done, as they've been created when the rocks were big and the water could move a little more, when the rocks are smaller and the water didn't have the oomph to carry its load. So there's a lot of things that you can see. And it's no surprise to me that esker or cames, they're probably cames as well, are deposited so close to Oak Hill. Okay. Now, something else we also see on Oak Hill is glacial polish or striations. I'm starting to find more and more striations around as I go on. This is on the Harvard Road side. And you can see that this rock it's pretty smooth, okay, pretty smooth. And I suspect it was ice as opposed to somebody coming around with high grit sandpaper, okay. Across the street, this is the Sanderson esker. I'm getting close to being done. This is the Sanderson esker. And the esker is a glacial deposition feature that when the ice is receding, streams, water is building up on top of the glacier, and it works its way down in the glacier through what's called a moulin. And eventually the stream, the river of water comes out of the glacier. And of course, the river of water is carrying a tremendous amount of sediment load, tremendous amount. And as it comes out, it will drop it in a very symmetric structure. The thing with an esker, it's very symmetric on both sides, great symmetry. And this is the Sanderson esker right across from Oak Hill. And we have Hartwell Hill has a nice esker, a little smaller. Mary Shepherd has one. The Sanderson esker, that's what we're looking at here. And the Smith property has a pretty large esker on it, what's left of it. called the Boxborough esker. Okay, and at the end of the, well, at the bend, I should say, of the Sanderson esker, there's a kettle hole, and that's what I'm standing in now. And you'll have kettle ponds and kettle holes. Like a kettle pond might be Spectacle Pond, for instance, where ice fell off the glacier and created a hole which broke the aquifer, if you will, and filled up. And the combination of the ice and the aquifer, you know, keeps the pond there. In this case here, the aquifer was not broken, so you have a kettle hole. Okay, now I'm at the Smith property here over on Wickham Avenue. And an interesting point here is, and this is right off Wickham Avenue, we're about from Oak Hill to the Smith property here, I believe it's 1.2 miles, the way the crow flies. 1.2 miles, maybe even a little less. And we are on the southeast side of the Shrewsbury Ridge. Okay, remember I talked about the Shrewsbury Ridge, that it's that high point, okay, of land on Oak Hill. Okay, and that actually, the Shrewsbury Ridge actually stopped that glacier, okay, from the water from going over it. The ridge was higher. Now, Black Pond has a near perfect circular pond, and that's my words, near perfect, that follows the general inflow and outflow direction of Tophet's Chasm in Oak Hill. I don't know what that means, but it's a point, it's a data point. Okay, but they're both following the same path. Some beautiful things that I'll see when I go into the Smith property is I see some beautiful pegmatite erratics. Okay, and these are erratic boulders that have probably been carved off of something like a lookout rock and transported on the ice. And this has on top some very interesting crystal formation. Okay, very interesting. And this is right off the main trail as you walk in. You'll see some very interesting crystal formation. And then following that, you'll see some really interesting bedrock exposures. And this, I believe, is the muckbrook schist. You can see some folding in this, see a little bit of folding. You can certainly see the laminations, you will, from the foliation as opposed to the initial bedding. This is more the foliation. But this is and notice the dip. I always notice the dip, okay? Notice the dip, how that's entering the ground. This rock, this is a point of contact. Remember I said at the beginning, points of contact are an interesting thing. There are two rocks here. You have a pen up here to show you the scale of it, but this is a pegmatite. I can see large pieces of milky white quartz and feldspar on it, and this black rock here. So I can see these white crystals with my eye, However, these black crystals are probably basalt or gabbro, which came up from the ocean floor. Okay, they tend to be dark, also known as a mafic, M-A-F-I-C material. And the crystals on this you cannot see with your eye. Okay, so you get a case here of big crystals tend to mean the crystals got to cool very slowly, so they grew. And small crystals occur when something cools really fast. Boom, really fast. Okay, like maybe they hit water, which basalt would. Okay, basalt would come out, boom, it's in the water, cools immediately. Here's some schist, which is the matrix, and some milky quartz, some kind of neat milky quartz issues. I'm almost finishing up here. There's some several suspected lime quarries in the Smith property, and I think they're more than suspected. I think they are, in fact, lime quarries. It's interesting to note that the dip on this particular quarry seems to be opposite the dip of other formations that I find on the property. Don't know why, but it's an interesting point. This lime quarry, looking down, I stepped it off at about 150 feet long, and then it breaks right here and then goes on back towards me for another 50 or 75 feet. But it's kind of deep, kind of, well, deep, kind of deep. It's 10, 15 feet deep, something like that. But I wouldn't go down there unless you were with somebody, maybe. Probably wouldn't be a good idea. But I thought they looked like lime quarries, and I said, how am I going to verify that? I said, I know. I'm going to go to the lime quarry in Chelmsford. So I went up there right off of Route 110, went to the lime quarry there. Very interesting take. Go check it out, and you'll see similar rocks. And this rock is indicative of Neshoba terrain, but it tends to be on the chlorite side. Okay, the chlorite side of things chemically, which means it's going to be used for lime. And these weren't full-scale lime quarries. These were used by local people for plastering and things of that nature. Okay, and then another lime quarry that I went to check out was up in Bolton. Okay, right off of Route 117. Beautiful, beautiful lime quarry up there. And I just started finding consistency between the type of rock here, the type of rock in Bolton. There's also lime quarries in Boxborough. Really all over the place when you start looking around. There's lots of vernal pools in the Smith property, just tremendous habitat, for fish and frogs to get going without a lot of predators, well, particularly frogs and salamanders to get going without a lot of predators. Here's that beautiful circular pond that I talked about, which is Black Pond, which is in alignment with Tophet's Chasm. Just to give you a link, when I came in the last hike I did with this on, actually when I came in this side and took this picture, I was with Art Lazarus. And this picture kind of gives you the sense of how steep that trail is down to the pond. There, I would not want to fall there. Okay, I would definitely not want to fall there. I'm probably 80 feet above there. Here we have some similar dip angles for two different rock types. The interesting thing about this for me is there's two rock types here. This looks like Tad muckbrook schist. Okay. This, on the other hand, looks like pegmatite. Okay, so it's reasonable to say that both those rocks got placed there at different times. They were probably formed at different times and placed there at different times, but they were both tipped, it looks like, at the same time. So can you see how relative ordering allows us to put together the sequence of events? Okay. Now, if you walk all the way down to Black Pond and you turn around, my back's to Black Pond now, I'm looking up at some great bedrock formations here. And I've been studying a little bit of what's going on here in terms of folding, just to understand that. Maybe I'll finish that up in this lifetime, maybe not. And then finally, my last slide is lots of glacial erratics that are on the Smith property. And I look at the one in the top right corner, it looks like a rat or a gopher or something, almost smiling at me with the nose and the eye up here. And I got a great rock here. And when I look at these, you see see where my cursor is here? Am I seeing folding here? Oh no, I'm going to have to go back there. Okay, so this is a great rock that shows mechanical weathering. This is about 6 feet tall. This is a big rock. And then one of my favorite rocks, it just looks elegant to me, is this nice little perched erratic that was left on top of a platform. Okay, and so that's it. Okay, I kind of got through that really fast with a lot of information, and so I'll take any questions that you have, and I'll stay here for as long as you want, and that may be longer than you want. but I'll be here as long as you want. So Helen?
I'm going to suggest if people either can raise their hand or if they can use the chat function, that might be the easiest to just type their question in and I'm happy to read it and you can answer it.
Okay, or I'll try to answer it.
Okay.
Okay. I do plan for people while we're waiting for questions, if there are any. I do plan next week, I'm going to be talking about the Prouty and Newtown Woods with kind of a focus on Newtown, the Yap property, a little bit of a focus on there. Okay.
I have a quick question. Can you hear me fine?
I can.
Okay. When my husband was young, many moons ago, they used to collect garnets up at Oak Hill. He
Sure.
has some that he collected with his dad.
Mm-hmm.
And I was wondering if you've ever found anything like that.
Well, I did. Some of my first slides, I don't know if you, perhaps you joined a little bit late, but I did in fact have some garnets that I found up on Lookout Rock and in other spaces, places throughout Oak Hill. But garnet is a very common mineral in metamorphic rock.
Mm-hmm.
And garnet has the characteristic that it's called an index mineral. And what an index mineral provides for us is it tells a geologist the depth and pressure that that mineral formed at. So, for instance, garnets will tend to form 5 to 7 miles down in the earth. So if we're looking at a garnet on the surface, like when I was at Lookout Mountain, well, it didn't, Lookout Rock, it didn't form there. It formed well below in the earth, and through erosion and uplift, it finally got up to the surface. I'm going to show you. I just so happen I can I reach over? Let me see if I can do that. Okay, I just got into freelancing, which I promised I wouldn't do, but I couldn't resist. But when you mentioned garnet, take a look at this garnet. I find these. Look at this garnet.
Oh, wow. Wow.
Okay, I find these all the time in New Hampshire. We have a place called Garnet Hill. And garnet was used for abrasive. It was an abrasive material.
Mm-hmm.
Okay. And yeah, they come in all different sizes. I mean, I've seen some garnets that are like this.
Wow.
Yeah,
Okay.
crazy. You can see the biggest garnets that I've ever seen is out at the museum in Amherst, Massachusetts. I forget the name of it, but anyway. So I hope that answered that question for you.
It did. Thank you.
Good.
Yeah, we just have some positive chat comments that say thank you is very interesting. Thank you. I think you probably, Bill, covered everybody's question. You're pretty thorough. I do have one question before we close because I want to make sure people that are still on hear this. Next week, you will be speaking of which properties at the same time?
Yeah, so next week I'm going to be, that will be Wednesday, right? On
Yes.
7 o'clock. And I'll be talking about the Prouty Estate and also Newtown Woods, which will really focus on the Yap property and a little bit of the Morrison extension and that area in there.
Okay, well, thank you very much. And next time I'm hoping to share a screen to show the books that the geology books that we purchased in honor of you doing this. So
well, that's wonderful.
Maybe I'll have them ready. Okay.
That's wonderful. And thank you all for attending, I hope. And if anyone has any questions, Helen has my email address and she can give it out to you. I don't care. Just, ask me the questions and, let's start up a conversation to talk about this. And I hope I can get out to get in the field to show you some of this stuff. That's where it's really fun. So thanks so much for attending.